Hello and welcome to zwitterstat. In today's video, we are going to discuss about properties of scalar multiplication in matrices, and we will also talk about how do we multiply two matrices. So just let's review what we have talked in the past videos. We have already talked about what a matrix is. A matrix is a rectangular array of numbers that is follow a particular order, right? And what's the purpose, why we are studying even matrices, and why do we need it? The basic need of matrices is to solve a system of linear equations, right? The linear equations may be in the form of ax plus by, uh, ax plus by, right? And sometimes we may have a system of linear differential equations, right? Linear partial differential equations or linear complete differential equations, which is defining a certain physical system, right? So the matrices eases us and gives a complete, not a, I can say like it gives us a neat picture to represent a set of equations, linear equations that are defining a particular physical system, right? So uh, in our uh, in our past videos, we also talked about how do we add two matrices, how do we subtract two matrices, right? And we also talked about the properties of matrix addition, that it is commutative, it's associative, right? So we will start in with scalar multiplication of matrices. So let's say I'm having a matrix A, 2, 1, 3, and minus 4. This is my matrix. And let's say I'm having a scalar. Now, what a scalar is actually? A scalar is a number, maybe a positive, maybe a negative, a number which we are going to multiply with this matrix A. So let's say I have a scalar, I have a scalar which I'm going to represent with lambda, right? I'm going to represent it with lambda, and let's say my scalar is minus 2, right? So let's say my scalar is minus 2, my matrix is A, where the first row has elements 2, 1, and the second row has elements 3 and minus 4, right? So, so now I'm going to multiply this scalar with that matrix. So here comes my scalar, here comes my matrix, and I can write it like this way. This is minus 2, there's 2, 1, 3, and minus 4. So what will happen is the scalar will be multiplied with each and every element of that matrix. So I can write it like this: minus 2 goes with 2 times 2, minus 2 times 1, minus 2 times 3, and minus 2 times minus 4. So my new matrix after scalar multiplication will be minus 4, minus 2 times 3 is minus 6, and minus 2 times minus 4 is 8. So this is my new matrix, right? So you see how scalar multiplication is done. The scalar is being multiplied with each and every element of my matrix, right? So now we have some properties for scalar multiplication as well. And let's just go through these properties in a so my first property is, let's say I'm taking this matrix only, and let's say my first property says that if I am a scalar, let's say k, let's say I take it lambda. So let's say my scalar is lambda, and it is being multiplied with addition of two matrices. So lambda is multiplied with a plus b, where b is some another matrix. Let's say 1 0 1 0 1. Now, matrix of this kind is what we call as an identity matrix, right? This is an identity matrix where the diagonal, it's a square matrix where the diagonal elements are 1 and all other elements are 0, right? So, let's say I'm having this matrix B, this is my matrix A, and let's say there's some scalar lambda. So, according to this property, I can write it like this. lambda times A plus lambda times B. Right. Now, if you remember from your study of numbers in your earlier classes, it's similar to the distributive property, right? If you have a number, let's say 2, which is being multiplied with addition of two numbers, let's say 3 plus 4. So we can write it like this: 2 times 3 plus 2 times 4, which is 6 plus 8, which is 14. Right. That's the distributive property of addition. We have already studied in our earlier classes, and the same idea is being followed over here. Okay, so I'm not going with the proof. I'm just giving you the simple idea. What are the properties of scalar multiplication? Right. The proof is simple. The idea simply follows. You can do that proof by yourself, and the proof basically follows the same idea that we have followed while proving commutativity and associativity of matrix addition, right? So we'll take the matrices A and represent it as Aij, similarly B as Bij, where Bij represents the element of the matrix B in the ith row and jth column. So we simply, when we add two matrices, it's simply the uh, addition of the elements that are occupying the same position in both the matrices, right? So we can write it like this: Aij plus Bij, and as we know, there is a lambda out over here with scalar. And now we know that when we multiply a scalar, each and every element of the matrix is multiplied with it. So we can write it like this now. Right. And now the same distributive property that we have studied for numbers, we will do that and do the same things in reverse. And we will be left with lambda times A plus lambda times B. Right. So we will now go with another property of scalar multiplication, which is, let's say I'm having this the scalar lambda, and there's another scalar, let's say L, and I am multiplying it with matrix A. So now I can write this thing as lambda times A plus L times A, right? No matter what your matrix is A, what your matrix A is, no matter what your scalars lambda and L are, this property will always be like this, right? This property will always hold true, and you can verify it. We can verify it. Let's say I take lambda is equals to 2, L equals to, let's say, -3, right? So lambda plus L is 2 plus -3, which is -1, and my matrix is, I'm taking this my matrix A as this. So lambda plus L times matrix A can be written as -1 times 2, 1, 3, -4, which I will get as -2, -1, -3, and plus 2. Right. This will be our resultant matrix. Now, let me erase this. Right. And I'm writing over here as lambda equals to 2 and L equals to -3. Now, you I have evaluated the left hand side of our property. Now let's just evaluate the right hand side. So let me change my marker. So on right hand side, I can write it like this: it is lambda times A, so lambda is 2. My matrix A is 2, 1, 3, -4, and and there is L, where L is, here L is -3, and A is 2, 1, 3, and -4. Right. So now we start evaluating. It's 4, 2, 6, -8, plus -6, -3, -9, and plus 12. Right. So now we are left with two matrices of the same order, 2 cross 2 and 2 cross 2, and we are supposed to add them. So now we will perform the addition and we get 4 minus 6, 2 minus 3, 6 minus 9, minus 8 plus 12. I hope it's visible. So uh, let me write this thing over here. This was from our LHS. Now, further evaluating our RHS, we get it as minus 2, minus 3, and minus 1, and this is plus 4. So you can see that, clearly see that the RHS is equal to LHS, right? So we have verified our property that lambda times whenever we have two scalars lambda and L and they are being added and multiplied with some matrix A, we get lambda times A plus L times A, right? We can write it like this. So we have verified with one example, and if you want to write a generalized some sort of proof for this, you can do it in the same way that we have done for uh, lambda times A plus B, the previous property, right? So we are done with the scalar multiplication of matrices, and now we will move on to our multiplication of two matrices, right? So here's the board. So let me change my matrix B, and let's say I write it as 1, 3, minus 1, and 5, right? So let this be my matrix B, and this is my matrix C. So let me show you first with an example how we do matrix multiplication, and then I will give you a generalized definition, not an exact definition, but uh, a statement that can that clearly uh, captures the idea of what is matrix multiplication is, right? So when we say two matrices are being multiplied, so let's say A is being multiplied with B. I write it as A multiplied with B as A times B, and we can write it like this times. Now for matrix multiplication, I will be going to mention the order of the matrices because it is very important to know the order of the matrices. Now, whenever we are talking about multiplication of matrices, the number of rows of the number of columns of the first matrix, here it's 2, must be equal to the number of rows of the second matrix, right? So this gives me the number of columns in the first matrix, and this gives me the number of rows in the second matrix. So it's highly important you first check the order of the matrix, whether the number of rows of the number of columns of the first matrix is equal to the number of rows of the second matrix, right? It's very, very important. Only then you can perform matrix multiplication, otherwise it is not possible, right? So whenever this condition is being satisfied, that the number of columns of the first matrix is equal to the number of rows of the second matrix, then we get a matrix whose order is given by the number of rows of the first matrix and the number of columns of the second matrix. So here the number of rows of the first matrix is 2. So the number of rows in my resultant matrix after multiplication is also 2, and the number of columns in the second matrix is 2. So the number of columns in my resultant matrix after multiplication is also 2, right? So this is one of the most important things that you have to keep in mind while performing matrix multiplication, right? So Let's just see how do we perform the matrix multiplication. So here, this is your, I will take the row of the first matrix and I will take the column of the first matrix. Right? I take the row of the first matrix and I take the first column of the first column of the second matrix, and now I'm going to multiply this element 2 with this element 1. 2 times 1 is 2, plus sign. Now I'm going to multiply 1 with this minus 1 and I will get minus 1. Now this thing will give me the first element in my resultant matrix. Right? Similarly, I take the first row of the first matrix and now the second column of the second matrix and do the same thing again. Let me give myself a little space to write this. So now 2 times 3, 2 times 3, and 1 times 5. Right. Similarly, uh, I will now take the second row of the first matrix and the second row of the first matrix and the first column of the second matrix, second row of the first matrix and the first column of the second matrix. So I will do the same thing again. 3 times 1 plus minus 4 times minus 1, and now using the same second row of the first matrix and the second column of the second matrix, I will get 3 times 3 plus minus 4 times 5. Right. So this will give me 2 plus minus 1, which is 2 minus 1, which is 1. This is 6 plus 5, which is 11. This is 3 plus 4, which is 7. And this is 9 plus minus 20, so which gives me minus 7. Right. So this is my resultant matrix after multiplication. Right. So this is how we do matrix multiplication. Now, I'm going to do the same multiplication, but I'm reversing the order of the matrices, and let's see what will happen. Right. So let me just give some space to write this. Right. New multiplication. So this was A times B, and now I'm going to do B times A. So B times A. Now B times A, what is my matrix? B, 1, 3, minus 1, 5. What is A? 2, 1, 3, minus 4. Right. So same thing again. First row, first column, and I will get this as, now 1 times 2 is 2 plus 3 times 3 is 9. Similarly, first row and second column, so 1 times 1 is 1 and 3 times minus 4 is minus 12. Similarly, minus 1 times 2 is minus 2 plus 5 times 3, which is 15, and now minus 1 times 1, which is minus 1, and 5 times minus 4, which is plus minus 20. So this is 2 plus 9 is 11, minus 1, oh sorry, plus 1, plus minus 12, which is minus 11, minus 2 plus 15, which is 13, and minus 1 plus minus 20 is minus 20. So what do you see? Is matrix B equals to AB? No, it is not at all equal. So what we can conclude from here, that it actually matters how do we multiply the matrices, in what order we multiply the matrices, whether we are doing A times B or whether we are doing B times A. It actually matters, right? Because matrix multiplication, it's not usually commutative, right? In some cases you may get a solution, you may get where A A times B is B time is equals to B times A, but it's not always true, right? So matrix multiplication, it's not usually commutative, right? So if it's not commutative, let's talk about associativity. So if I talk about associativity of matrices, so let's say I'm having a matrix A, this is a matrix B, and there's a matrix C, right? So if I do matrix A times matrix B times C, then it will be equal to matrix A times B times C, right? But it will not be equal to matrix A times C times, right? So it's not the it's not associative in the way numbers are. Like let's say 2 times 3 times 4, right? So what does it give me? 3 times 4 is 12. So 2 into 12, which is 20, right? Okay. Now let's say I can write it like this: 2 times 3 into 4, which gives me 6 times 4, which is also 24. And now write it this way: 2 times 4 times 3, right? So what gives? It's 8 times 3, 20. So in multiplication of numbers, associativity holds true very strongly in the sense, if I write like this way, that 2 times 3 into 4 inside the brackets, or 2 times 3 inside the brackets and then I multiply it with 4, and 2 times 4 inside the brackets and then I multiply it with 3, in all the three cases I get 24 as the result, right? But this is not the case with the matrices, right? If I do B times C and multiply it with A, and do A times B then multiply it with C, then I will get the same result. But if I do multiply matrix C with A first, then I will not get the same result. And the reason is because here you can clearly see that the order B, or the order in which B and C are being multiplied, is reverse. And we have clearly see that matrix multiplication is not commutative usually. So it's not possible, uh, or I can say it's not always true that A times B times C, or A times B inside brackets times C will be equal to this thing, right? So it's because of commutativity, which is not usually true in case of matrix multiplication, this property will also not be true. So associativity holds weakly for matrices, right? The order in which the matrices are being multiplied needs to be taken care, right? So these are some of the things that we have to take care when we are talking about matrix multiplication, right? So let's just review a quick summary what we have talked about today. So we talked about matrix multiplication, we talked about scalar multiplication. In scalar multiplication, we talked about some number, which may be a positive or negative, is being multiplied with a matrix, and we get a resultant matrix in which each and every element is being multiplied with that scalar, right? Now, we had some properties for scalar multiplication we discussed, and we tried to give a short proof for all these things, right? Then we talked about matrix multiplication. Now, matrix multiplication is not the does not take the hold the same properties as we multiply two numbers, right? 2 times 4 is equals to 4 times 2, but a matrix A times B, it's not usually equal to matrix B times A, right? So it's not usually commutative when we do matrix multiplication. And similarly, we saw that associativity of matrix multiplication, that associativity holds weakly for matrices, right? Matrix multiplication, right? And it's because the matrix multiplication is not commutative. We have to take care. And the most important thing, when we are talking about matrix multiplication, we have to see that the order of the matrices holds a great importance, right? So if I'm having a matrix A, which is 2 1 3 1, and let's say I'm some matrix 3 1 1 2 2 1. So here I'm having 2 rows and 2 columns. Here I'm having 3 rows and 2 columns. So here you see the number of columns of the first matrix, and if I'm sorry, this is my matrix B, and if I have to evaluate A times B, so the number of columns of the first matrix is not equal to uh, the number of columns of the first matrix is not equal to the number of rows of the second matrix. So A times B cannot be evaluated, right? I cannot evaluate A times B. But if I have to evaluate B times A, then I will write B first, and then I will write A. So here you see that the number of columns of the first matrix becomes equal to the number of rows of the second matrix, and here the matrix multiplication can take place, right? So the order of the matrix holds a great importance when we are multiplying two matrices, right? So you have to take care of the order, you have to see the order, and by and if you have to in some questions it is usually asked, what is the order of the resultant matrix if I multiply a matrix A which has an order m cross n and matrix B which has an order n cross p, then the matrix AB will have the order, it will have the number of rows same as the matrix A and the number of columns same as the matrix P. So it will be of the order m cross P. Right. So this much for today. In the next video, we will talk more about matrices, and in the next video, I will try to solve some of the example on matrix multiplication, addition. Right. So till then, take care. Bye bye.